Greetings to you, welcome to physics class. In today's video, we'll be looking at a brand new topic, the structure of the atom. And so, under the structure of the atom, we'll be looking at models of atom, energy, quantization. By the end of this study, you are expected to define an atom, discuss different models of atom, and hence draw and label them. Explain what is meant by continuous spectra and line spectra. Tell what quantum jump is. Explain with suitable diagrams emission and absorption spectra during quantum jumps. Define energy quantization. What we are trying to achieve in today's lesson is to follow these scientists who took their time to study what matter is, to discover the topic energy quantization. Energy quantization is a topic that is taught at the A level as quantum physics. And so we want to look at the basics behind the discovery of this branch of physics, which is also taught at the secondary school level as energy quantization. And so let's begin this way. Introduction. In our SS1, we defined physics as a natural science that deals with the study of matter and its motion through space-time and with the concepts such as energy and force. The study of physics at all levels is actually based on this brief definition. It's generally known at this level that matter is anything that has weight and can occupy space, and that solid, liquid, and gas are the three states of matter. Hence, a deep study of what matter is by various scientists gave birth to what we call energy quantization. The group of scientists that sat together and come up with this stuff, energy quantization, everything began with the Greek philosophers. Philosophers are a group of thinkers. In those days, they would sit and be observing nature and be asking themselves, what is this? What is this? How? How does this behave? Where does this go? And so they will ask themselves all these questions, and then they will come up with one solid answer. And so let's begin with the Greek philosophers. The early Greek philosophers studied matter and postulated that matter is composed of atoms that are finitely divisible. Michael Faraday also in 1834 carried out his studies on the subject of matter and discovered that matter is not only composed of atoms but is also electrical in nature. Before I continue, this was a trend of research in those days. In today's world, what we love to do is copy and paste. A will research his work. When B come, B will now copy A's work and paste in his research projects with no improvement of what A has done. It wasn't so in those days. I want to be challenged and to be encouraged and to be motivated by this group of scientists. This is one thing I want you to learn in this video. How to improve on people's work and bring the best from those work. How to criticize people's work constructively and not destructively. This was what research was in those days, not what we have today as copy and paste, copy and paste. The current research we have right now from various graduates in various universities, if you ask me, is an ancient of days research work. There's no improvements. I don't want you guys to be doing that. Always improve on people's work. So let's continue. So this was what Michael Faraday did. He studied this. He didn't just agree that matter is just composed of atoms that are finitely indivisible. He carried out his study and discovered that matter is electrical in nature. This was his contribution to the study of matter. Matter is electrical in nature. And so he proved that the electrical nature of matter can be physically seen through certain chemical change when electric DC current is passed through certain solutions, a process he called electrolysis. So you see, today we are all enjoying the application of electrolysis. Had it been Michael Faraday just came up and read what these guys, the Greek philosophers, discovered about matter and was contented with what they discovered, and matter composed of atom. That's right. That's okay. Today, the wristwatch I am putting in my hand here is a product of electrolysis. You see that? Product of electrolysis. The jewelries women put on their neck, the necklace, all that they use to beautify their body is electrolysis. I call it the physics of beauty. So Michael Faraday is the brain behind the physics of beauty. He's the brain behind the physics of beauty because he refused to agree with the Greek philosopher that matter is just composed of atoms, but electrical in nature. So let's move on. Who was next on line? Other curious scientists came up again and were asking themselves, if this matter composed of atom, then what is this atom? What is an atom if matter is composed of atom? The second question on board was, what constitutes an atom? And then the third question was, what is the structure of the atom? How does this atom looks like? This atom, number two, what are those things that makes up this atom? And so these questions were begging for answers, and the answers needed to be given. These questions were begging for answers, and the answers needed to be provided. So answers to the above questions. The first person that attempted to answer this question was John Dalton. John Dalton, 1766 to 1844, only attempted to answer question number one by saying atoms or ions are the simplest component of matter, and that an atom is an indestructible, invisible sphere. That was his contribution. And he was acclaimed the father of atomic theory by the science community. Do you think that was all? That was not all. Henry Becquerel, this guy came up and said, you Dalton, you say an atom is indestructible? I don't agree with you, Dalton. This is my contribution. After studying what matter is, or that atom you say is, I discovered that this atom can disintegrate. This atom can also decompose to form other atoms. You see that? And Henry Becquerel gave birth to what we call radioactivity. You see that? Radioactivity. Was that all? That was not all. This guy came up, Henry William Crookes. William Crookes, 1895, attempted to answer the question on what constitutes an atom, the constituent of an atom, in the discovery of his cathode ray in electric discharge tubes. William Crookes revealed that atom constitutes of negatively charged electrons, and that Gas discharge tubes, take note of this point, gas discharge tubes. The fluorescent tube you see around, this is their working principle. Gas discharge tubes under low pressure and high electric potential can conduct electricity in some way. This was William Crookes' contribution of what atom, of what matter or atom is. So the next person on board was a community of science. The community of scientists now came and sat together and tried to combine the definition of the Greek philosophers, the definition of John Dalton, the definition of the Greek philosophers, the definition of this guy, and also the definition of this guy, and they were able to come up with something like this. This was what they came up with. So based on this research study by these various curious scientists, it was therefore agreed by the community of scientists in 1900 that matter consists of atoms. This was the contribution from the Greek philosophers. Atoms, which contains electrons. This was whose contribution? This was J.J. Thomson's contribution. And then electrical also in nature. Atoms as a whole is what? Electrical in nature. Matter consists of atoms, which contains electrons, and that the atom as a whole is electrical in nature. So that was how a concise definition of what matter is was gotten from the various contribution of these scientists. Now, that was not all. J.J. Thomson in 1904 thought about the findings from his colleagues and said, oh, this neutrality of an atom means that there must exist within the atom enough positively charged components, that is proton, to balance the negatively charged component, electrons, discovered by William Crookes. And so the research went on. The research went on until J.J. Thomson came up with the first structure of the atom. So with such super thoughts, the physicist J.J. Thomson was first led to propose a structure of an atom, which we call atomic model. He visualized the atom as a whole, as a homogeneous sphere of positive charge inside of which are embedded negatively charged electrons, as can be seen here. With just one inspiration, neutrality in the definition of atom, this guy was motivated to come up with this structure. What is your contribution in science? What is your contribution in science? I don't want you to be a scientist that will just pick up something, read, and be satisfied with what you see. Be that scientist that will dig deep to discover new things from what one person have discovered and then to improve on it. So that was not all. This guy came up, Ernest Rutherford. Ernest Rutherford and his team studied J.J. Thomson's work, that is at his atomic model, and performed a series of experiments whose result contradicted Thomson's model. What was their research work? In Ernest's experiment, a beam of positively charged alpha particle was directed at a thin sheet of a metal foil. It was discovered that most alpha particles pass through the metal foil without deflecting, as if the metal foil were positively empty space. Were mostly empty space. However, only a few of them were diverted from their path, and some of these few actually rebounded backward, as can be seen here. This is what this guy discovered in his experiments. Now, in one of the videos, a guy was asking me, sir, what is alpha particle. Alpha particles are positive in nature. Now, in physics or in science, we know that like charges repel from each other, and then unlike charges attract each other. This was a principle with which this guy was able to discover something new from an atom. So alpha particles are positive. So as they hit here, some of them bounce back. This bouncing back is telling you that there is something here that looks like alpha particle, making them to repel and move in the opposite direction. And so, look at them here once again. The alpha particle hits a positive particle at the center and then rebounds back. So, the rebouncing of this alpha particle and scattering as they enter the center of this gold foil motivated this guy to say something. Hence, Rutherford discovered that the scattering of alpha particle by metal foil was a repulsion from a heavy positively charged nucleus present in the center of the atom of the metal foil. This totally contradicted Thomson's model of atom, which supposed that the distribution of the charges, protons and electrons was different. That was a neutral. So by this, Rutherford was moved to propose a planetary model of atom, which suggested that the atom consists of positively charged heavy core called the nucleus, where most of the mass of the atom was concentrated. Around this nucleus, negatively charged electrons cycle in orbit, which cycle in orbit much as planet moves around the sun. Each nucleus must be surrounded by a number of electrons necessary to produce an electrically neutral atom, as can be seen below. So, Ernest Rutherford is the brain behind the discovery of the nucleus of an atom. Can we clap for this guy? And so, this is Rutherford's model of atom. Here there are nucleus. This is the nucleus of the atom that contains the neutron and the proton. So the alpha particle is positive. As it hits the positive proton here, it bounces back. So this was the discovery that brought the birth of the nucleus of an atom. So at this time, a Danish scientist, Niels Bohr, studied in Ernest's lab and discovered two main difficulties about Rutherford's model of atom. Niels Bohr studied Rutherford's work and discovered that there were some things that needed to be improved. What were those things? Let's look at it. That Rutherford's model predicted that light of a constant range of frequencies will be emitted as charged particles, that is electron, moving in a field of opposite charges, proton, loses energy. This was called continuous spectra. But experiment shows line spectra. That Rutherford's model also predicted that atoms are unstable electrons quickly spiral into the nucleus, since there is an attractive force between the oppositely charged nucleus and the electrons. But atoms in general are stable, since matter around us is stable. So these were part of his finding. Let's move on. So based on these loopholes, Niels studied Rutherford's work and discovered these loopholes. So Niels in 1913 opted to modify Rutherford's planetary model of atom by suggesting a model of hydrogen atom with three postulates, namely, the electron will move round the nucleus in certain specific circular orbits called energy levels. And the centrifugal force due to the motion will counterbalance the electrostatic attraction between the electron and the nucleus. In such orbits, the electrons will move without radiating or losing energy. For these orbits will also be called stationary states. And the higher the energy of the electron, the farther its orbit from the nucleus. So this was Neil Bohr's hydrogen model of atom. Here is the nucleus of the atom, where you have the neutron and the proton. And then here is the electron revolving around the orbit of this atom. Now, between the electron and the proton, there is a force of attraction. There is a force of attraction that connects the electron to this nucleus, the center of the atom. So, the energy of an electron in an atom cannot vary continuously, but will be restricted to a limited number of discrete or individual values. By this, the energy of an electron is said to be quantized. What do you mean by quantized? That is, have only one discrete value. Also, the electron in an atom cannot lose energy continuously, but must do so in quantum jump. In such quantum jumps, photons of light will be emitted only if the atom is from higher stationary states or higher energy level to a lower energy level or stationary state. Please kindly take notes of this particular stuff. Read this stuff 10 times to understand what this means, so that you will not be confused. So the energy for a single photon of light in such quantum jump, quantum jump here simply means the transfer of electron from one energy level to another energy level. It is either from higher to low or from low to high. So the quantum jump, as discussed above, is given mathematically as HF is equal to E subscript U minus E subscript L. We call this our equation number 1. Equation number 1 is named line spectrum equation, where E subscript U and E subscript L refer to upper and lower energy states or levels of the atom. F, this is small letter f, small letter f. F is called what? The frequency of the emitted photon of light, and H is the Planck's constant. Emission and absorption spectra. From the beginning of this lesson, we were saying that we will be asked to define what emission and absorption spectra is. So let's quickly look at this before we move on. An electron emits energy when it is transferred to a lower energy level, that is excitation. Alternatively, it absorbs energy when it is transferred to a higher energy level. These are two atoms, two hydrogen atoms, analogized to explain the Bohr hydrogen atom model. Now, E1 here stands for a lower energy level, a higher energy level, highest energy level. You see that? So when electron jumps from a lower energy level to a higher energy level, the electron absorbs energy. Hence, the photon of light you see with the arrow pointing inside. When electron is transferred from a higher energy level down to a lower energy level, E1, the electron emits light, a photon of light, as you can see here. So this is what we mean by quantum jump. The journey from here to this place is a quantum jump from a higher energy level to a lower energy level emitting light photon. The jump from here to here is a quantum jump from a lower energy level to a higher energy level absorbing light energy or absorbing the photon of light. So this is what we mean by quantum jump and also emission and absorption spectra. So his third postulate or a postulate he brought up to improve J.J. Thomson's work was that the third postulate of the Bohr model was that the angular momentum values of the electron in an atom are quantized. That is, they are restricted to a limited number of discrete values that are integral n, multiples of a constant, the Planck's constant h, 6.626 exponential negative 34 jouleseconds, divided by 2 pi. Mathematically, angular momentum L is equal to n into h over 2 pi. We call this our equation number 1, where n is equal to 1, 2, 3, 4 to 4 to infinity. The numbers here stand for integers or quantum number. As you can see here, this could be n1, n2, n3, n1, n2, n3 in that order. That is what we mean by this. So hence the quantization of angular momentum first proposed by Bohr is the key to modern atomic theory. So at this point, we can confidently define energy quantization. Energy quantization is therefore a phenomenon that describes the radiation of light energy, and take notes, that describes what? The radiation of light energy and the gain or loss of energy in an atom during radiation as not a continuous quantity but rather a discrete separate amounts or packets of energy that occur only during a quantum jump of an electron from one energy level to another. Max Planck in 1902 was able to show the energy E of one quantum of radiation or photon mathematically as E is equal to hf. The above equation, number 3, is known as Planck's theory of radiation, where E is energy, h is Planck's constant, f is the frequency of radiation, and the factor hf is equal to the value of energy quanta or discrete packets. So Planck's quantum hypothesis Planck's quantum hypothesis hence suggests that the energy of radiation can be E is equal to hf, E is equal to h2f, E is equal to 2hf, E is equal to 3hf, E is equal to 4hf, and so on and so on. E is equal to what? nhf till infinity. Meaning that there cannot be vibrations or radiations whose energy lies between these values, expecting that the radiation is not a continuous quantity but rather quantized. This is a very, very important point here. Not a continuous but quantized. That is only exists in discrete amounts. To this, we have come to the end of today's class. When next we meet, we shall be looking at atomic energy level, photoelectric effects, Albert Einstein's equations of photoelectric effects, and we're gonna do a whole lot of calculations. Thank you. Stay safe. Stay blessed. God bless you.